Assalamualaikum and a very good morning to everyone. So today we are going to learn the last chapter in Form 5. That is chapter 8, Mathematical Modeling. And in this chapter we are going to learn two learning standards. The first learning standard is to explain what is mathematical modeling, and the second learning standard is to solve the real life problems through mathematical modeling where involved is function linear, quadratic or exponential, and also to communicate the mathematical modeling process implemented. Okay, so why must we learn mathematical modeling? Okay, this chapter is very important to the real life problem. Okay, for example, to predict the future population growth. Okay, the future cases of COVID-19. Okay, this is where they got the R0 values. Okay, and the coming cases, the prediction of coming cases in 2 weeks. Okay, so this is the use of mathematical modeling. Okay, so now let us see what is the meaning of mathematical model. It's a representation of a system, okay, or a scenario that is used to gain qualitative or quantitative of some real-world problems and to predict future behavior. Okay, so more or less it's like a formula we derive from the information and the problem that we have. Okay, now let's consider these two following problems. The first problem: the population of town A is 40,000. It is known that 45% of the residents in the town practice the habit of recycling used plastic drinking bottles. If each person in the town uses 5 plastic drinking bottles per week, how many bottles are recycled each week in the town? So for this, the first problem, it's easier for us to just calculate the solution, okay, because there are enough information in the problem. But for the second problem, how long does it take to clean up an oil spill in the ocean? There are no enough information. We need to gather information. We need to collect data. We need to do assumption. So this is where mathematical modeling is applied, okay, for this kind of problem, this kind of open-ended question. So in doing the mathematical modeling, there are a few components that is very important. Okay, the first one is to identify and define the problem. Okay, so when we have a situation and problem, we need to identify what information that we have and define the problem in the situation. Okay, the second component is to make assumption and identify the variables needed to solve the problems. Okay, then the third component, we will apply mathematics to solve the problems. Okay, this is where all the skills that we learn in mathematics, we'll be using it at this stage. Okay, next, the fourth component is to verify and interpret solutions in the context of the problem, meaning that we will relate the mathematics solution with the real world problem. Then we must do reflection. Okay, if there is a space for improvement or it's not accurate or not okay, then we need to do or repeat the process. Okay, but if it is okay and acceptable, then we will report the finding. So report the finding is the sixth component. Now let's look at the real world problem. The grocery store, which is far from your house, sells a pack of 10 kg rice at a lower price than the one closer to your house. Is it worth the drive or the cheaper deal? Okay, so the first component, we must identify and define the problems. Okay, so what are information that we need to solve this problem? The price of a pack of 10 kg rice and the cost of petrol, the distance from the two stores to your house respectively. We need also to find the information needed from the internet. For example, the price of a pack of 10 kg rice from each store, the distance of each store from your house, the current petrol price, the car's petrol consumption rate, and so on. Next component is to make assumption and identify the variables. So these are the assumptions that are made for the real world problem. The first assumption is we assume the route between the house, store A and store B is a perfect straight line. Then we assume drive car to the stores, and the third one to assume we purchase the same number and brand of price at store A and store B. Okay, after we make the assumptions, now these are the variables needed in the mathematical model. Okay, you can use any relevant capital letter or small letter. Okay, let's say S is the distance between store A and store B. P1, the price of a pack of 10 kilogram rice at store A. P2, the price at store B. M, the petrol consumption rate of the car in kilometer per liter. N, the number of packs of 10 kilogram rice to be purchased. H, the current petrol price in RM per liter. S, the difference in price in RM for purchasing the pack of 10 kilogram rice at store B as compared to store A. And T is the difference in the cost of petrol in RM for driving to store B as compared to store A. Okay. Now, the next component is to apply mathematics to solve problems. Now, from the information that we got maybe from the internet, okay, so the price of a pack of 10 kilogram rice from store A and from store B, okay, now let the quantity of 10 kilogram rice to be purchased be 2 packs, okay, so the price we pay is, okay, do the calculation with time with 2, okay, so from here we know that we can save 3 ringgit and 92 cents if we buy at store B. But don't forget, okay, other costs that involved in this purchase, that the distance between store A and store B be 6 km, the petrol consumption is 17.6 km per liter, and the current petrol price is 2.08 per liter. So the petrol needed for the 6 km route is 0.341 liter, and the cost of petrol is, okay, 1 ringgit and 42 cents. So the amount that we save is actually 2 ringgit and 50 cents. Okay, when we buy 10 kilogram rice at store B. Now, the next component is to verify and interpret solutions in the context of the problem. That means from the mathematics solution, we relate to the real life problem. So, the resulting mathematical model is as follows. S and T, this is the formula where we get from the mathematics solution just now. And if S greater than T, then it's sensible to drive to store B to purchase rice and save more money. What is S? Okay, S is the amount that we save when we buy the rice. Okay, so if S greater than T, T is the cost of petrol. Okay, so if S greater than T, of course, it is sensible to drive to store B. But if S less than T or equals to T, then we should not drive to store B to purchase rice. Okay, so since that, in our case, S greater than T, so we save more money by purchasing rice at store B. Hence, it is sensible to drive to store B. Thus, the mathematical model is able to solve the problem. Now, the fifth component is to refine the mathematical model. We have to do reflection on the mathematical model just now. So the assumption made regarding the route between the house, store A and store B is a straight line needs to be revised. If the route between the three places is not a straight line, how does this impact our model? If new assumptions are being made, then the model needs to be revised to reflect this change. Okay? If needed, we need to repeat the process. And the last component is to report the findings. Okay, so to report the findings, okay, we will use the symbol and diagrams when necessary to report the findings. Okay, the symbols and diagrams will depict the whole modeling process until it leads to results. Every model has strengths and weaknesses. What is important is that the model identifies those strengths and weaknesses in the report. Okay, for example, the value of a person's time is not considered in this model. Is it worth driving an extra 12 km for someone to save 2 ringgit and 50 cents? According to this model, saving 5 cents is considered worthwhile. The model did not account for any environmental considerations. Okay, is it environmentally responsible to drive an extra 12 km just to save 2 ringgit and 50 cents? This model did not account for environmental efforts such as efforts to reduce carbon emissions. Okay, so this can be included in our report. Now let's proceed with some more example. Okay, Jeremy saves 4,000 at Bank Bunga Raya with a simple interest rate of 1.5% per annum. Jeremy wants to buy a computer worth 4,455 ringgit with his savings. How long does Jeremy need to save? Okay, so question A, identify and define the problem. Okay, that means we need to understand the problem. So in this problem, we know that the principal and the interest rate. Okay, we are given the principal and interest rate. So the interest from the saving is the amount that Jeremy needs beside the 4,000 to buy the computer. We need to determine how long Jeremy needs to keep his savings in the bank. Okay, question B. Determine the assumptions that need to be made and identify the variables in solving the problem. So this is the second component, to make assumption and identify the variables. So assumptions that we make is we need to assume that the interest rate does not change during the period of our interest calculation. Otherwise, the formula I equals to PRT will not be appropriate. Okay, remember this formula we have learned in Form 3. Okay. We also need to assume that the price of the computer does not change when Jeremy has raised the required amount of money. Okay, so by the time he wants to buy, the price of the computer is the same. Okay, then what are the variables involved in this problem? The variables involved are I for interest, P for principal, value, R for interest rate, and T for time in years. Okay, now let's try with the question in self-practice 8.1a. The journey of a boat moving upstream which covers two places located on the riverbank takes 6 hours. The return journey of the boat moving downstream takes 5 hours. If the speed of the river current is 2 km per hour, what is the speed of the boat on calm water? Question A. Identify and define the problem. So to understand the problem, we know we are given information about the distance of two places and the river current. And what we need to find is the speed of the boat on calm water. So this is the answer for question A. Now for question B, determine the assumptions that need to be made and identify the variables in solving the problem. So the assumptions that we made is the speed of the river current and of the boat will remain the same, and we also ignore the wind resistance that would affect the speed. Okay, and what are the variables involved? V for the boat speed, T for the time, and S for the distance of two places on the riverbank. Now let's proceed with the second learning standard on how to solve real-life problems through mathematical modeling, okay, that involves linear, quadratic, and exponential functions. Okay, now if you can still remember, we learned linear function. It's a graph of a straight line where the variables is to the power of 1. And the quadratic function, the graph is the form of parabola. Remember the minimum and maximum shape. Okay, and this is new for you, exponential function. Okay, so this is the example of the exponential function. Y equals to 2 to the power of x, and it starts from 1. Okay, so this is the general form. Y equals to ca to the power of x. C is the initial value, and a is the base, like shown in the diagram. Now let's look at example 2. Amin traveled 405 kilometers on 45 liters of petrol in his car. If Amin wishes to go to a place which is 198 kilometers away by car, how much petrol in liters does he need? Solve this problem through mathematical modeling. So if you can remember, we can solve this problem using the variation skills that we learn in variation. Okay, but this question asks us to solve through mathematical modeling. That means we have to do step by step. Okay, we begin with the first step to identify and define the problem. So we know that in this question we need to determine the volume of petrol required for 198 kilometers. And then we also know that the farther we travel, the more petrol we require. So the amount of petrol varies directly with the distance we travel. Now, the second component is to make assumption and identify the variables. So we assume that the driving speed for both routes are the same, and the variables involved are x and y, where x will represent the distance traveled and y represent the amount of petrol required. And since this is the question, the amount of petrol, so y as the subject, and we know that y varies directly with x, so in equation form, y equals to kx, where k is a constant. So if you can see from the equation here, okay, this is a linear equation. So the function involved is a linear function. Now, the next component is to apply mathematics to solve the problems. So here where we use the skills that we learned in variation. Remember, we substitute the value of y and x to get the value of k. So we will get the equation. Okay, from the equation, we know that x equals to 198. So we substitute x with 198. So we will get the amount of petrol that is y 22 liters. So we know that 22 liters of petrol is required to travel 198 kilometers. Okay. So next component, to verify and interpreting solutions in the context of the problem. So we need to relate the situation with the solution that we need just now. So we may not be able to use the linear function model in all situations. For example, if the 405 kilometer route is through towns and cities, and 188 kilometer route is through highway, okay, so the car will use up petrol at a faster rate in the first route compared to the second route. Okay, so when this is translated to the real world situation, the linear function model obtained is not suitable to solve this problem. Okay, so we reflect to what we have done just now, okay, to get the solution, and we know that this model is not suitable to solve this problem for the different situation. Okay, so the fifth component, to refine the mathematical model. In this problem, we are not able to refine the model due to limited information given. Okay, and lastly, to report the findings. Okay, we will report the findings as the solution that we had done in the preceding sections. Next, look at example 3. The diagram below shows the cross-section of a river. A hydrologist measures the depth of the river 1 meter at different distance, x meter from the riverbank. The results obtained are given in the following table. So the table shows the distance from the riverbank and the depth of the river. Now show how the hydrologist uses the data above to determine the depth of the river through mathematical modeling. Okay, the first step, as usual, identify and define the problem. So we need to determine the depth of the river, okay, when we are given some information about the distance and the depth of the river. Next, to make assumption and identify the variables, we assume that the river is the deepest in the middle with the depth decreasing to 0 at the edges. And the two variables involved in the study are the depth of river y meters and the distance from the riverbank x meters. Okay, next component, to apply mathematics to solve the problems. So we write the distance from the riverbank and the depth of the river as a set of ordered pairs and draw a graph for the data. Okay, so if you can see here, we got the graph of quadratic. Okay, that means this involves a quadratic function. Okay, in mathematical modeling, to represent the actual situation, the approximate value is used. Based on the graph, the depth of the river is 3 meters, when the distance from the river is 15 meters. Okay, so this is the deepest of the river bank. So the next step is to verify and to interpret solutions in the context of the problem. So from the graph just now, we know that it is a quadratic function graph, and this is the general form for the quadratic function. We do not know the value of a, b, and c, so we need to substitute 3 coordinates in order to get the value of a, b, and c. So from substituting the value of the coordinates, okay, we will get c equals to 0, and then a equals to negative 0.0136, and b equals to 0.408. So we substitute all the constants value into the quadratic function general form, okay, and this is the general form for the quadratic function. Now, We need to substitute x equals to 15 in order to get the depth of the river. Why x equals to 15? Because from the, if you can see from the information here, okay, the depth of the river 0 when the distance is 0, and it's again 0 when the distance from the riverbank is 30. That means since that this is a parabola graph, the middle is the deepest. So the middle of the data x from 0 to 30 is 15. That is why we substitute x equals to 15 to find the deepest of the river. Okay, and we will get 3.06, approximate to the answer obtained from the graph. Okay. And now we need to define the mathematical model. For this model, we assume that the river is the deepest in the middle. This may not be true for some other rivers. A new model will be needed if we have new assumptions. And the answer will be more accurate if more data have been collected. Okay, this is what reflection that we do after we get the mathematical model. And then lastly, we need to report the findings from the beginning to the ending in a proper way with the variables and diagrams needed and also the data collected. Okay, last example. Okay, compound interest is interest that is calculated based on the original principal and also the accumulated interest from the previous period of savings. At the beginning of a year, Mr. Gomez saves 20,000 in his savings account with an interest rate of 4% per annum, and the interest is compounded once a year. Derive a mathematical model for Mr. Gomez's total savings after 3 years of saving. Solve this problem through mathematical modeling. So again, using the mathematical modeling, we need to do it step by step from the first component until the sixth component. And actually, we have learned also this in Form 3 about the compound interest. Okay, if you can still remember. Okay, so let's look at how we do the mathematical modeling to solve this problem. First component, to identify and define the problem. Mr. Gomez is given compound interest, which is compounded once a year, and his principal is 20,000, and the yearly interest rate is 4%. This is the information that given in the question, and derive a mathematical model for Mr. Gomez's total savings at the end of 3 years. Okay, this is what the question asks you to do. Next, to make assumptions and identify the variables, assume Mr. Gomez did not withdraw or raise his savings throughout the period of saving. This is the assumption that we make. Okay, then the variables are principal amount, R and P, yearly interest rate R, number of times the interest is compounded, N times T years. Next, we apply maths to solve the problems. Okay, keep in mind that when calculating the compound interest, each year we have 100% of the principal plus 4% of the previous balance. We construct the table as follows. Okay, because the compound is once a year. Okay, so for the first year, the principal is 20,000. The interest received is 20,000 multiplied by 0.04. This is 4% of the previous balance. So the total of principal plus interest, okay, is 20,000 plus 20,000 multiplied by 0.04. If you factorize, take out the 20,000. So in the bracket is 1 plus 0.04. Okay, so amount of savings, okay, this formula becomes 20,000 multiplied by 1.04. So this is the amount of savings of Mr. Gomez the first year, but it will become the principal of the second year. Okay, so now the principal is 20,000 multiplied by 1.04. So interest received, this is the principal multiplied by 0.04. So principal plus interest again. Okay, we factorize 20,000, and what we'll get is 1.04 multiplied with 1.04. So this is the total of savings of Mr. Gomez. 1.04 multiplied by 1.04, that means 1.04 squared. Okay, if you can see, the power here relates to the year here. Now, this is amount of savings in year 2. It will become the principal amount in the year 3. Then this is the interest received, principal and interest, the total and amount savings. Okay, 1.04 to the power of 2 multiplied by 1.04, that means 1.04 to the power of 3. Okay, and the same goes with the year 4 and 5 and so on. So that means the amount savings here, the power 1.04 is related to the year. Okay. Now, let's verify and interpret the solution in the context of the problem. Based on the table above, at the end of every year, the amount of savings is a power of 1.04 times the principal, and the power corresponds to the number of years of saving. So we can generalize this pattern to a mathematical model, okay, by letting P represent the principal, T is the number of years, and R represent the yearly interest. So this is the mathematical model to get the amount of saving at the end of the year. Okay, so from the formula, okay, since that the power T, okay, so it's an exponential function. Okay, and this is the graph of the exponential function. Now let's refine the mathematical model. Okay, so this is the model that we got just now from the solution. That is for annual compounding. But in reality, the interest is often compounded more frequently, for example, compounded semi-annually or quarterly. So if the interest is compounded monthly, the interest rate is divided with 12 months. Okay, because 1/12 of the rate is applied each month. So the variable t in the exponent is multiplied by 12 because the interest is calculated 12 times in a year. Hence, the mathematical model becomes, okay, this is the new formula, if it is compounded monthly. So in general, if the interest is compounded n times per year, the mathematical model is, so this is the general mathematical model. Okay, and lastly, report the findings in the proper way from the beginning to the ending of solution. So now try yourself with the self-practice 8.1b, textbook page 240, and also the extensive practice question 1 and 2 in your textbook page 242. Now we have come to the end of the lesson. So remember, in this chapter there are 6 important components, okay, in order to do the mathematical modeling. The first component is to identify and define the problems, meaning that we need to know what are the information given and what is the question. Then the second component, to make assumption, okay, and identify what are the variables needed to solve the problems. The third component is to apply mathematics to solve problems. It may involve linear function, quadratic function, or exponential function. The fourth component, to verify and interpret the solution in the context of the problem. Relate the solution with the real life problem. And then we do the reflection. So if we need to refine the mathematical model, we will repeat the process. But if it's not needed to refine the mathematical model, then we just report the findings. Okay, so that's all for the topic. Okay, so if you have any problem, you can contact us at any time. So all the best and thank you.